Okay, so today we're going to start to talk about a slightly different topic, which relates to the processing of large amounts of dynamic data or streaming data. So thus far, we've focused on processing these sorts of repositories or static collections of data in files, large collections of data using Hadoop and Spark and so forth. So this is what we would refer to as batch processing. So we take a large file and we process all of the data in the file. Also, in terms of querying, for example, these large files. We'll talk more about that later in the course, NoSQL. However, we also have applications or scenarios where the data are moving, constantly changing. So we refer to these as streams of data. So the type of techniques that we need in the case of streaming data are different. So we can consider event processing, where we have streams of events of things happening, producing this stream of data that we need to process. Continuous querying, in the sense that rather than send a query and then get our results over the data, we might like to register a query and have some continuous results produced from that. And also a key feature of processing streams is the idea of real-time response, that actually we want to, in real time, be able to react to the data that are coming in. So briefly, to go through some key kind of application areas of streaming data. So we could consider social media analytics, where we have events, might be a kitten video goes viral, or we might have a burst of tweets about earthquakes. Um, so these are events. Continuous querying would be maybe, for example, to track the sentiment for a company's products. So I'm constantly tracking what social media is saying about my products, monitor popular users tweeting about me. So I want to see if some very influential person tweets about me. Real-time response might be, for example, in the case of tweets about earthquakes, to put emergency services on alert, or maybe in the case of poor sentiment about a company's products, to schedule a quality control review to see, okay, are these users who are making fun of my product, do they have a serious point? Another key application, a more technical low-level one, is in terms of log monitoring. So in complex information systems, in the context of large companies who deal with lots of applications and data, they have all these logs, and it can be difficult to make sense of all the logs that are out there. So log monitoring is an important application for streaming data as well. So events would be, for example, a burst of log messages. All of a sudden we have this huge burst of log messages, or some critical error message stating that the system is going to go offline, or some data is going to be corrupted, or some important message that we need to take care of. Continuous querying would be maybe, for example, to track the most critical fixes today, to monitor memory leaks in the new release, or monitor a certain type of error or exception in the new release. Real-time response might be to disable an unsafe feature in a website, maybe to automatically fire the new developer if there are lots of memory leaks in the new release, and so forth. So finance is also a major application area, which involves dynamic data, streaming data. So event processing, company goes public, new IPO, or some stock drops sharply in value, for example. Continuous querying might be, for example, to track the stocks with gains of 10% in one day, or create alerts for major buy-sell transactions where a lot of a stock is dumped or bought. What's the opposite of dumped? I don't know. So real-time response might be to buy as quickly as possible or sell as quickly as possible before a stock gains or loses value. A question about, will we study non-relational data like video or audio in this part of the course? In general, no, we're not going to touch multimedia, nor will we touch data mining, but we will look at relational data, and we'll look at text and unstructured data. Applications of streaming data. So there, we're talking about how to process kind of dynamic streams of data. Yeah. Another key application, one that's very important to the Universidad de Chile and universities in Chile in general, is that of astronomy. So event processing in this context, a telescope might move, or maybe a light source, astronomical body might flash or move, for example. Continuous querying would be to find possible supernova based on essentially the light that's perceived from an object. Supernova, I think the light signal changes over time, or to track an object that's moving, right? So something that's actually moving across the sky. Real-time response would be maybe refocus a telescope on an important object, for example, a possible supernova, or to lower data filter thresholds. So often in astronomical data, where we receive so much raw image data, light data, that we can't actually store everything. So often we'll have a kind of a filter to say, okay, there's nothing interesting here. We're not going to store this or process this. But if we detect an interesting object, then we might say, okay, let's store all of the data we can get from this region of the sky. And also, you may have heard of Internet of Things, which is this concept where everything will have a URL and IP address. Your toaster will be able to tweet on your behalf on your account and so forth. So essentially this idea of all these smart devices that are interconnected, and also smart cities where buses are connected to railway stations and so forth. So event processing, in this case, a light turns on, for example, and that means maybe certain other appliances should be also turned on, or maybe it starts to rain. Continuous querying, tell me when the temperature reaches 30 degrees Celsius, for example, or update the position of a vehicle. So give me the updated position of the vehicle as it moves. Real-time response might be turn off the air conditioning in a building, take another route. So very briefly, this is started to give some context of some ideas of where dynamic data are playing an important role. Any questions? Okay. So to deal with lots of streaming data, what we need essentially again is some sort of distributed platform, because if we try to process streaming data all on one machine, we would eventually reach the limits of what is possible on that one machine. So we're going to talk about some distributed streaming platforms, and one in particular, right? So there are actually now quite a lot of frameworks available. There's Apache Flink, Apex, Storm, Spark, and this one here, which is a K for Kafka. So the one we'll focus on, and they all have a similar sort of purpose. They have different trade-offs and strengths and weaknesses. We'll just speak about one, and the one we'll speak about is Kafka. Not just because it has a cool name, but I added this class maybe 3 years ago to the course. And I chose Kafka because it was being used in it's quite a popular option, first of all, but also it's being used in the university. There are researchers working on astronomical data using Kafka. So in the same AMA, oh, there's a cat coming to visit us. Hello, cat. I think she's okay. She's actually interested to hear about Kafka. There she is. Go away now. So Kafka essentially is a streaming platform. It's a popular platform, and it's being used in the university in the Apache project, if you've heard of that. So I chose to focus the class on this, but the same sort of techniques apply, or the same concepts apply in the case of other streaming platforms. So okay, let's focus on one application, which is the idea of emergency response. So where we have essentially some sort of disaster going on, and we need to respond to that disaster. So if we think about this in terms of real-time emergency response, We might have different agencies that are interested in different streams of data, fire brigade, the health service, ambulance service, the police, for example. And we have different streams of data that might help them to be more informed about what's going on in terms of an ongoing emergency. So this might be, for example, seismograph, earthquake information. We might have weather information, a stream of whether it's sunny, whether it's raining, what's happening with the weather. Hotline in terms of calls to an emergency service, to the police or to hospitals. Twitter, for example, people tweeting about how they perceive the earthquake, where the fire is spreading to, and so forth. And we have news outlets that are, producing some news about the ongoing events and some traffic information, which would be important for the emergency services to get to a particular location. So we have all these different sorts of streaming data, and obviously this is a very complex picture, right? We might also have some databases. So we might have a database of geographical places in Chile, for example. And we might also have maybe a database that is recording some sort of stream of events and reactions to different events. So somehow a record of what's happening. So we have streams of data, we have some databases, and then we have our emergency services. So we can start to think, okay, for the fire department, all of these streams here are relevant. Somehow they need traffic information. They need to know about the news. They need to know about where the fire is spreading. They need to know about what calls are coming in. If it's going to rain or not is obviously very important to the fire department, and also maybe information about where an earthquake was most felt. Maybe the health service is only interested in the hotline information and the traffic to make sure their ambulance gets there. And let's say that the police department's more interested in the last four here. So as well as that, they need information perhaps from the databases with respect to the timeline of events or the locations, the maps. And let's say as well that there's some interdependence between these different services. So the fire department might need to inform the health service or the police department about certain things that are happening. The police department might need to inform the hospitals about accidents and so forth. So what we end up with is this sort of spaghetti of dependencies of different types of data with dynamic data, databases, even the services themselves can be producing and consuming data. So what we need is somehow a way to better organize this, to avoid this sort of spaghetti of dependencies. And a sort of maybe or obvious solution perhaps would be to put something in the middle. So we put something in the middle, and then we feed our data sources into that. And that allows us then to stream the data to the relevant consumers, those who need the data. And we can also then connect to databases, for example, if necessary. And those that are consuming data may also produce data back, which goes to some other place. So the core idea here is to use a framework that allows us to route data to who needs it. So we can have lots of consumers, lots of producers, also connections to static databases, for example. And we can also have services clients, clients that are both consuming and producing data. So putting something in the middle to coordinate the data will avoid this sort of spaghetti that we saw earlier. So this thing in the middle here is, in this case, Kafka, Apache Kafka. Apache Kafka comes from, is named after the author Franz Kafka, at least I presume it is, where if we look at Google Trends, we see that Apache Kafka is currently winning in terms of popularity. Apache Kafka is an open source project, as we can tell by the name Apache, implemented in Scala Java with the JVM, and it originated in LinkedIn. So the people of LinkedIn started to develop Kafka. So as an overview, we saw this concept already of having various consumers and producers, right? So we have these producers that are pushing data, they're writing data to Kafka, And then we have these consumers that are reading data from Kafka. Okay. So these are the two main sort of clients. There are different things we can connect to Kafka, but mostly we have producers and consumers are the most important. Okay. Oh, something happened to my animation. So we see that the producer produces a message, and that message might end up going to multiple consumers. So in terms of the data model used by Kafka, is there any questions before we continue? No. Okay. So how does Kafka model data? How does it model these messages? So we have the notion of a Kafka record. So essentially what we have is these messages, which consist of 4 elements. So these are created by producers in Kafka, and then they will be read by consumers. We have an offset, which is just the order of the message. We have a timestamp, which is the real time in which it was written to Kafka. We have a key and we have a value. Okay. So what we do is these represent events and they're immutable. So once they're written, we can never change them. We can't go back and change the value for a given key, for example. We'd have to write a new record. So they contain an ID, which is the offset, timestamp, a key, and a value. So the timestamp is assigned by the application or Kafka. So the timestamp typically represents the real Unix time, let's say. So Kafka ledger is then composed of a sequence of records. So these records are written over time by one or more producers, and they form essentially this ledger of records. So the producers here may only append to the ledger. They can only write to the end of the ledger, which is similar to, for example, distributed ledgers like blockchain and so forth. Yeah. So consumers, on the other hand, can theoretically at least read from anywhere. So consumers can read from anywhere, kind of. So we'll have to see what that means. But typically, consumers will read in the same order in which in the order of the ledger. Okay, but they can, under certain circumstances, read from anywhere. So we'll have to talk about that. So consumers can potentially replay ledgers if they want to. They can go back. Maybe they can. Maybe if they went offline, they can replace some of them, the records, the messages that they got while they were offline. So a key. Any questions or? So producers can only append. All of these records here are immutable. They can't be changed once they're committed to Kafka. The consumers in general will read in the same order, but they can potentially replay or read things in a different order if they want to, if they need to, depending on certain configurations that we'll see. Okay, so Kafka considers then the notion of topics, and a topic is essentially just this idea of having different ledgers for different types of topics, different types of messages. So you might have a topic that is relating to disasters, for example. We might have another topic related to news. We might have another topic that's related to traffic. And we can have one or more producers or zero or more producers writing to each topic and zero or more consumers reading from each topic. So for example, disasters, maybe the earthquake information, weather and hotline is of relevance. The news, maybe Twitter and the news stream, and traffic, maybe Twitter and the traffic stream, maybe also weather, but okay. And then these different services, the consumers can consume the records from the different topics, as we see here. So producers publish to topics, and we say that the consumers subscribe to topics. So we can talk about subscribers to different topics. Okay. So topics are persistent, so which means that they're stored on disk. And generally, we're going to be using the disk to store the messages that have been received. And we have a configurable retention policy, which means that we can set we can have some policy in terms of what messages are kept, what messages are removed, whether we keep older data or not, and so forth. So the first option is to keep everything, so we don't delete anything at all. This is, great if we have enough space, we can remember everything. But one would imagine that if we have maybe limited resources, or we have a massive stream of data, perhaps this might not be feasible with the available resources. So another option is to delete once consumed. So once some consumer has read um, some record, that record can be removed. This would be the other extreme. This is essentially, get rid of it as quickly as possible. So another option would be keep for a period of time. So for example, if we're reading temperatures from a sensor, we'll say, okay, keep the temperatures for the last um, um, day, for example. And then maybe outside, rather than storing, temperature readings every second, we can store an aggregate value for each hour or something like that. But here we just say, okay, we'll keep the records for a day, a week, a month, a year, or whatever, and then start to purge the older messages. Or we can set it to use a fixed amount of space. So we can say, okay, I'll assign 1 terabyte of storage to this topic. And as we reach the end of that, the older messages in the ledger will be removed. So again, this just lets you somehow configure what data you want to keep with respect to the resources you want to use. Okay, so the topics as well can be partitioned across machines. So this is the distributed aspect. So in brief, we've already seen this concept quite a lot. So the default partitioning is by key. So we can actually decide which machine will index which record in a topic based on the key of the record. Okay, so we see that here we have 3 partitions. This is all actually the same topic, right? The same, all in the same topic. So one thing that's of note is that we partition by key. So I'm putting this one superscript here to say somehow that this is in partition 1. Okay, so we assume that all these keys hash to the same partition here. Here we have the keys for partition 2, and here are the keys for partition 3. So another thing of note is that the offsets are as they were before, in terms of we have a guarantee that these offsets will correspond to the order of the timestamps here. So within each partition, we keep the ordering. The problem is that across partitions, we have 1, 1, 1, 2, 2, 2, 3, 3, 3. So we're not really sure which message comes first. In the global order, we might lose information about which record came first. Did this one come before this one, or this one here, for example? So essentially ordering or offset, this is the 1, 2, 3, 4, 5, 6, is guaranteed per partition, but not across partitions. We can't decide the order across partitions based on the offset. However, for ordering across partitions, we can use the timestamp. So the timestamp essentially is this number here, which is the real time, the Unix time. Now, that might not be as reliable in the sense that we might have messages that arrived at the same time, or we might have, there's no notion of a global clock. So maybe there's some maybe 5 nanosecond difference between the clocks on 2 different machines that will produce this discrepancy. As we mentioned in the second class, there's no global clock can be assumed. But in general, we could say that, okay, if we're not sensitive to messages being out of order at the sort of nanosecond level, and if we're okay with there being ties in terms of timestamps, then we can use the timestamp as a global ordering across partitions, and it would probably work perfectly fine for most applications. Any questions or doubts? Okay. So topics can be replicated. So we spoke about partitioning before, but we also spoke about the importance of replication, particularly in the context of distributed file systems. So what we need to do is we need to choose our factor of replication. So typically a good factor is 3, right? So we spoke about how 3 can be used to distinguish in case there's an error in 1, then we don't have a tie. Right, so 3 is a good minimum number of factor for replication. So, but we can choose this factor per topic. It could be 1, it could be 2, it could be 3, it could be whatever we choose. And then there's some automatic load balancing in terms of which machine will store which partitions and which replicas of partitions. So here we see we have partition 2, partition 2, partition 2 on one machine, partition 3, partition 3, partition 3, and on this machine we have partition 1, partition 1, partition 1. So we have the partitions are distributed across the machines and replicated in this case by a factor of 3. So this generates something of a problem, the idea of replication, which is the idea that we now have to coordinate across the replica certain information. Like we guarantee the order within each partition of the offsets. So given that we have 3 different partitions, if we have consumers writing or producers writing here and writing here and writing here to the different machines, we could lose that guarantee of order. So it means that we have to be very careful to make sure that we can provide the guarantee of order. And also we need to be able to know in what order a consumer is reading. So we'll talk a little bit more about that later. But essentially we have to be able to coordinate carefully between these replicas to ensure some consistency of the order in which messages are written and received. So how do we do this? Well, we've actually seen similar-ish problems before in the context of distributed file systems and so forth. The idea is to elect a leader. So one of these partitions will be chosen as the leader for this partition, okay? So the other partitions are then followers. So this partition here is then a follower of this partition, and we have a leader as well for partition 1 and for partition 3. So the leader has to do a lot more work for that partition, but the idea would be that every machine is the leader of some partitions. So essentially it ends up sort of balancing out, okay? So it's not that one machine is the leader of all of the partitions, but rather each machine can be a leader of several partitions. And ideally that would be balanced. So the leader is automatically elected also based on load balancing to ensure that somehow the leaderships are balanced across the different machines. Okay.
Sorry?
Yep.
Why do we need leaders?
So if we go back to here, we see we have, okay, so we have a partition here of the ledger, right? So we have to imagine now that we have 3 copies of the partition. So we have 3 machines for this one partition, for this partition 2 here, for example. So one option would be that you just have the 3 machines that are completely equal. They're just replicating all the data in this partition, this part of the ledger. So to which machine should we write messages? So what we could say, let's write, the consumer can write to whatever machine is closest. So whatever machine is closest to it, the consumer, if there's machines in different regions, like there's machines in the US and Asia, for example, you say, okay, just write to whichever of the 3 machines is the closest. But if different consumers are writing it in parallel to different machines, then we won't be able to keep the order, right? So there will somehow it will create all these complications in terms of making sure that we don't have 2 consumers writing a different message 8 on the different machines in the different locations, for example. So we need within each partition to ensure this offset ordering so that this is the 8th message, for example. So one other option would be to say, okay, well, actually, rather than having all 3 machines being equal, let's nominate one of those machines in the replica to be the leader. And that will coordinate essentially the order in which messages are received. So in that way, then that machine can take care of the order and say that, okay, this message will be message 9, and then it can forward the message to to the other machine. So I'll talk a little bit more about that in detail, but that would be the main objective, to ensure this order.
Thank you.
Okay. And also to ensure some other details that we'll see later, but yeah. So consistency of order of writing, but also of reading, but we'll come to that later. Okay. Any other questions or? Okay. So we have to worry about order. So the kind of standard solution we've seen to this in other settings has been to elect a leader, and that leader coordinates somehow the data for that partition. So it somehow controls the state of that partition. So this helps us to ensure the correct order, consistent order per partition. So the reads and the writes are then to the leader. The requests are made to the leader. So in terms of the write guarantees, we can have different types of guarantees. So the first type of guarantee is called asynchronous or no guarantee. It's essentially that the producer will just send whatever data, let's say it's going to partition 1. The message will be received by the leader of partition 1, and that's it. Essentially, the producer then doesn't wait for any acknowledgement. It just sends the request to send this to partition 1, and that's it. It assumes somehow that the write is successful. Okay, so this is the lowest guarantee, we could say, somehow asynchronous. A second option is that we request that a leader commits. So what this means is that the producer writes to the partition, and then the write is considered to be successful when there is an acknowledgement that the leader has received the message and has committed to its partition. Later, this leader will send the writes to the replicas. These are called followers of partitions, but to the replicas of the partition. But it does not wait to make sure that they have correctly received and acknowledged the writes. Okay. So the third option is commit plus a quorum. So we can set the quorum to whatever we like, but here we'll have a quorum of 2. So what this means is that we want the leader to commit, and we also want 2 other machines to commit. In this case, it happens to be the number of replicas. So what we expect in this case is the producer sends the write, then the partition will send the write, whatever the record is, to the replicas of the partition. It will await their acknowledgement, and then only then will the leader acknowledge. So we'll acknowledge that at least 2 other machines have acknowledged the write. Okay, so this is somehow a stronger guarantee that the write has been done. So why do we have these different options? Why not just go for the most secure one, right? Why not just make sure all the time? Why not just have some very high quorum? So the problem, of course, is that we have more network use. We have more messages to send, and we have to imagine that we could be writing, millions of tuples every minute, for example, or maybe even every second. So we have these different options as a trade-off. So asynchronous is the most efficient. Yeah, so there's no guarantees. We're not sending any acknowledgements back. So it has a very low latency, but we send it and we hope it's been written, right? So we have no guarantees that something has been written. This would be pretty good if we're working within some sort of application that's sort of robust to dropping some records. For example, if we're computing trending topics on Twitter, and we drop 1 in every million tweets because of a network error or something like that, we actually don't really care all that much. It's probably nobody's going to notice, and it's not going to affect the results all that much. Okay, then we have this sort of intermediate option of leader commit. We at least wait for the leader to acknowledge the change. So we know that the write has been made at least persistent on the leader. But it has this medium latency, right? So we have to wait for the leader to write to the disk and to be able to acknowledge that it has made that change persistent. This is not an ideal guarantee either, because the leader could fail soon after doing this commit. So the best guarantee is the leader commit plus the quorum n. So this requires the data to be persistent on the leader plus an additional n machines. But again, it has this high latency where we have the disk writes. Okay, these are in parallel. We don't need to do n writes in sequence, right? But we have these the overhead of these disk writes plus the network messages and acknowledgements to make sure that n machines have acknowledged and written the message, the record. So this sort of application, this would be good maybe for trending topics on Twitter. Asynchronous leader commit plus quorum n would be good for, you know, emergency services where they're receiving streams of calls, or you know, something where you really do not want to lose any records. Okay. Any questions or? Okay, so we're coming to the kind of second part of the class. I think I'll pause here rather than start the next section. So we're having a slightly longer class, but I think we'll be able to finish. So let's say until 3:20. It's maybe an extra long break, but break until 3:20. Any questions or comments or doubts? So it makes sense? Okay, so I'm going to see what's wrong with this cat meanwhile. So talk to you at 3:20. We'll finish the class then. Okay. Oh, I've lost the chat. Let me try that again. Where's the chat? Here we go. It seems I've lost the chat. This is very frustrating. The chat disappears behind my presentation. I have no idea why it does that. Alt tab. Okay, yeah, okay. So, okay, we were speaking about writes. So let's talk about reads. So we have consumers who are reading from the ledger from a particular topic. So Kafka's role is to track the consumer offset. So it will remember which offset the consumer is reading from. So in this case, let's say that the consumer decides to read record 1 and 2. So it reads these two records. Excuse me, we're just going to assume that it reads values that are equal to the offset just to make life easier. These could be messages or some other type of record, but we'll just assume that it's reading the same value as the offset. So it reads 1 and 2, maybe into memory, for example, or to its local disk. Continues 3 and 4, 5 and 6. So Kafka is remembering that consumer 1 currently has read 5 and 6 and so forth. So we have to be careful though, because in a distributed setting, we always have to be aware of the possibility of failures. So in the case of failures, we need to have some sort of way of dealing with those failures. So how do we do this? Actually, there's a number of options of how to handle these sorts of failures, this sort of situation. So what should we do in the case of a read failure? So Kafka offers different types of read guarantees, much like we saw it as different types of write guarantees that might be better for different types of applications. So the first type of read guarantee, and the most efficient, is at least once. So actually not the most efficient. The most efficient would be at most once. So at least once. So it guarantees that each value, each record will be processed by the consumer reading the entire ledger, the entire topic, that each record will be processed at least once by that consumer. And the consumer offset is updated on the consumer acknowledgement. So the consumer will acknowledge and then the offset will be updated. So how does this work? So the consumer reads a value and then it sends an acknowledgement to say, okay, I've read values 1 to 2. And then Kafka will remember, okay, consumer 1 has read values 1 to 2. So then it will read the next two values. And let's say there is an error on reading the second record. Okay. So here we have 1, 2, 3, and we're missing 4. Okay. So what the consumer will do, it will not send an acknowledgement. Instead, it will request the read again. It will, this time, let's assume that it reads 3 and 4 again. It will acknowledge back to Kafka that it has read 3 and 4, and then the offset will be updated. So if we look at the values that it has read 1, 2, 3, 3, 4. Okay. So it can continue in this way. So it reads 5 and 6, assuming everything's okay. It acknowledges, and the offset, consumer offset, is updated by Kafka. So we see that this is called at least once, because if we fail, for example, reading 4, it will read 3 again and 4. So here we see that we've read all of the values at least once, but we've read 3 twice. So this is the at least once, where we repeat a read that has failed. Okay, so this is one guarantee. This ensures that we see every message at least once. Okay. A different type of guarantee is so the at least once guarantee, I should mention, would be good in applications like maybe emergency services, where you want to have a register of every call that was made. And okay, it's not the end of the world if you process the same call twice, but you need to make sure you process each call at least once. A second guarantee is at most once, where we guarantee that each value will be processed at most once. So the failure, it's when, for example, the 3 partitions fail to deliver the data. So yeah, it could be a network error, for example. It could be some other type of error. It could even be the consumer error. So this error here might be because the consumer somehow went offline, or right at that point had a network error, or whatever it might be. But somehow there's a failure to read that value. Be it a problem with with Kafka, a problem with the network, a problem with the consumer. So it didn't fully read all of the records it had requested. Yeah. So at most once, perhaps intuitively refers to the idea that we'll read, we won't repeat any reads. So let's say we read 1 and 2, fine, okay. So that's okay. So then we read 3 and 4. So essentially the offset is moving as the read is being done. It's not waiting for an acknowledgement. It's just moving the offset as the data are being read. So let's assume we have an error here. Well, okay, under the read at most once guarantee, we just move on to the next one, 5, 6, and it just ignores the fact that there was an error. So we see that we're missing 4 here, but we see that all of the messages we've read at most once. So again, this might be okay, for example, for computing trending topics on Twitter, where if we miss a tweet, it's not the end of the world. And this would be more efficient because it's not waiting for an acknowledgement to update the offset in Kafka. So somehow the offset is being updated asynchronously. Okay, so there are some other types of read guarantees that we can have, which is, there is one called effectively once, which is sort of maybe intuitive. When we saw the first guarantee, we might have thought, okay, why can't the consumer detect the duplicates, which they can. So it's at least once, but the consumer takes care of duplicates. So it works in a similar way as at least once, which is that the offset is updated on an acknowledgement from the consumer. So in the case of 3, 4, for example, when we read that and fail on 4, the consumer doesn't send an acknowledgement, but rather rereads from the current offset. and then it's updated to 3.4. As a result, we see that we have initially on the consumer 1, 2, 3, 3, 4, but we assume that the consumer will detect the duplicate and say, okay, on the consumer side, I'm not going to consider 3 twice. I'm going to apply some process to remove the duplicates. So this is essentially a practical way in which one can get an exactly, simulate an exactly once guarantee. Okay, so and then it continues in that fashion. So the consumer again is the one responsible for making sure that everything is read exactly once by using the at least once guarantee and then deduplicating records locally. Okay, so the exactly once, the idea is it's more expensive. So exactly once the idea is that, okay, it's not the consumer's responsibility to remove the duplicates, but somehow the framework itself should make sure that everything is read exactly once. So what happens is that the data and the offset will be updated as a single transaction. Somehow everything is transactional. So it means, like in a relational database, a transaction is considered to be an atomic operation that either the entire operation passes or the operation fails. And there's other guarantees, like in ACID as well, that two transactions cannot interfere with each other in a weird way. But essentially, that's the idea, that we're going to update the offset and do the read as if it were one atomic operation, a transaction. That's either fail completely or succeed completely. Okay. So what happens in this case is that we have two actions. We have the read and we have the acknowledgement that updates the offset. Okay. And this is considered using transactions to be one atomic operation that will either succeed completely or fail completely. Okay. So this is the exactly once idea, that we have this sort of transactional support. So in this case, because the first step of read fails, the entire transaction fails. Okay, which means that it's not considered successful. So then we have the next read and the next acknowledgement and so forth. So by using these transactions, we can give a sort of an exactly once guarantee that everything is read as exactly once. This is the most costly overall, because now we have this sort of transactional cost associated. So it's somehow the strongest guarantee, but also the most expensive. Okay, any questions or doubts about that? Que era ac es acknowledgement, como conocimiento, reconocimiento, como es a message to say that, yeah, it's been processed. It's just short for acknowledgement. Other questions? Okay. So why do we have these different guarantees? Again, the idea is that we have different trade-offs of stronger guarantees are less efficient, weaker guarantees are more efficient. The weakest guarantee being at least, no, at most once, sorry, and the strongest guarantee being this exactly once. Okay. So we spoke about leaders of replicas before. So we say partition 2 here is a leader of, or this machine is the leader of partition 2, and this machine here is a leader of partition 1, and this one is a leader of partition 3. How does it work with reads? So with reads, in fact, okay, the producers write to the leader, but the consumers also read from the leader, okay, which is maybe not so intuitive. One might think that the consumers could read from any replica, the closest replica, whatever is the most efficient for it to read from. But that's not the case. So it reads from the leader. Why is that? It could be that the leader as well has to somehow maintain not just the order of the reads, but also of the writes, but also the reads in terms of maintaining the offsets of the consumers. So this ensures that the consumers are reading everything and can have their read guarantees. Of course, this comes at a cost because, maybe there's one partition or one replica of a partition that could be more efficient to read from, but always reading from the leader helps us to ensure the guarantees that we spoke about previously. Of course, as well, it's worth mentioning that it shouldn't become too much of a bottleneck for one machine, because every machine should be the leader of a different partition. So somehow we can balance the load that way. Okay. So that's the idea of reads and writes with partitions and leaders. So we have that's sort of the core of Kafka, what we've seen, but we also have some additional features that can be useful. One of those features is called a consumer group. And the idea of a consumer group is that we can register multiple consumers and say that all of these different consumers form the same group. And we can say that it's sufficient for any one consumer in a group to read from something. So essentially the idea is that we just want one of these consumers to have consumed or acknowledged that message. So we can have multiple consumers subscribe to a topic, and we just have to make sure that at least one consumer in each group processes that. So what this can allow is sort of it can effectively allow us to partition the consumers. So we could have different consumers that might be different machines or in different locations. And it allows for load balancing within each group, right? So we can somehow manage groups of consumers that will take equivalent actions in this way. Okay. So consumer groups. We also spoke at the start about the idea that producers can be consumers, and we can also have databases. So we spoke about this idea of having these databases perhaps as well, and also the idea that, for example, a consumer can also be a producer. So we've seen the producers and consumers, and here we call a consumer that also produces data. So we have the connectors first for the databases, for external data sources. And then we have a notion of an API for things that are both consumers and producers called streams. So these can consume from a topic and push back messages to that topic afterwards. So the producer API, essentially what their producers can do, they can just append records to the topics. So they can push records to a topic. Consumer API can read records from the topic. They can pull the records from a given topic. So a connector API allows for reads and writes to external components. So that might be a connector to a database, a connector to another streaming platform, and so forth. So the final type of API is a stream API, which is essentially just like the union of the producer and the consumer API that allows, as the stream API allows a client to both read records from the input topics and append records to output topics. So it acts as both a consumer and a producer. Any questions or? So we're almost there in terms of Kafka. So what other optimizations do we have? So there are various types of optimizations. I won't get into the details too much on that, but we have, for example, different forms of log compaction where repeated sequential values are suppressed. So, you can do something like an interval encoding. For example, if you have a stream of data coming from a sensor that's a temperature sensor, a thermometer, it might be the case that you just end up reading every second the same temperature and it doesn't vary, right? So you can have long sequences of exactly the same temperature. So these sorts of situations can be relatively common. So Kafka has a special process by which it can sort of compress all those and say, okay, from offset 1 to 55, the temperature was just 12.4 degrees Celsius, for example. Direct disk to network. So rather than going through, as we mentioned at the start, Kafka is implemented in Java Scala. So it's implemented to run on the JVM. but it has certain optimizations where necessary, or where possible, it can simply stream the data directly from the disk to the network without needing to parse it through the JVM to produce the network response. So it can read data directly from a disk and send it over the network. For example, data from a ledger. There's also things like consumer producer quotas, which set limits to avoid saturating the system. So essentially you say, okay, each consumer can produce a maximum of 1,000, can read, or each producer can write a maximum of 1,000 records per second, or each consumer can read at most 1,000 records per second. So this is to ensure that no one producer or consumer is saturating the system, and so on and so forth. There's quite a few optimizations implemented as part of Kafka to ensure more efficient processing of dynamic data. There's also within the Streams API certain other features that might be useful. For example, we can do some sort of aggregation to count different types of messages. We can do joins, which allows us to unify two streams. So if we have two different streams and we want to join their keys, we can do those. We can do that in Kafka. This obviously comes at a cost. When we're trying to unify two streams, we have to synchronize the two streams and join on the keys and so forth. There is also windowing, which allows us to define a retention period. It allows us to essentially somehow cache and store data that we can refer to later if we want to go back in time. So we can do that with this windowing feature of Kafka. This is just to give some idea of what other sorts of things we can do. We can also do continuous querying, which uses a special query language similar-ish to SQL, which allows you to register a query. But the typical database scenario is you send a query, you get your responses back immediately over static data. In the continuous querying scenario, you register your query and it will send you responses as new answers are found, new solutions are found, they're sent to you. So this obviously has quite a high overhead as well in terms of continuous querying compared to simple processing of streams. So there are some available frameworks. Again, there's Flink, Apex, Storm, Spark, Kafka, but a lot of the same concepts that we've spoken about in this class apply equally to all of these frameworks. Some of the frameworks may not offer all of the same guarantees. For example, exactly once may not be offered by some frameworks. There are different trade-offs in terms of how the data are processed and so forth. But Kafka is a good example of, what these frameworks are doing is not all that different to what Kafka is doing. Yep. So that's Kafka. I still would like to talk a little bit about projects, which will take maybe 5-10 minutes, but I'll take any questions about Kafka if there are. Okay. Why don't read write on different machines to avoid collisions? In what context? So in general, why not read write on different machines? The core idea is that you want to read in order. So if you're reading and writing freely from different machines, you might lose that order. So you have different replicas of the topics on different machines. Let's say you have 3 machines copy every part of a partition. So those 3 machines should keep the same data in terms of the partition. So if you're reading and writing kind of from different machines in parallel without synchronization, without saying, okay, this message came before that message, or this write came before that write, or this read came before that read, you're going to lose the guarantee of the order of the offset per partition. And you could also lose the guarantee of the order of the reading, for example, or the guarantee of reading at least once, at most once, exactly once, and so forth. So that requires some coordination. So for example, you need some machine to coordinate the offset of the consumer. So for that reason, in general, it's not possible to just have different reads and writes on different machines, because you need to have one global value for the offset, have one global value for the offset of the writes, the offset of each consumer in the reads. I'm not sure if that addressed the question. Okay. Any other questions? Okay. Projects. So briefly, let me see. We have some time, yeah. But just to briefly mention about projects, mostly we'll coordinate the projects in the forum to not take too much time from the class or from the labs. We'll coordinate mostly on the forum, but just to give an introduction to projects. So with the projects, you've seen enough topics that you can start to think about what topic of what kind of project you'd like to do. So you could, you've already seen Pig, MapReduce, Spark, Kafka now. You can also do projects based on what we'll see later in the course, but it's a good time to start to think about that. So as mentioned in the first class, it's 20% of the mark will be dedicated to the class project. So it's essentially a group project that you'll have to do, which will be done in threes, maybe fours. We can, depending on how many people there are and how things work out, but done in groups of 3 or 4. The goal will be to use what you've learned in the course to hopefully do something cool and fun and interesting. So the topic is completely up to you, and it's quite flexible. So the process, form groups of 3 or 4 in the forum before April 30th. So I'll start a thread in the forum after the class where you can either propose your names or you can, the names of some group, or if you prefer, you can wait and we'll do a random assignment of the rest. So you can start to think up some interesting topics or find some data sets. You can register your topic in the form. The idea is that there shouldn't be 2 groups doing a very similar project, essentially. So first come, first served. The first group to post the idea will kind of book it, so other people can't do something very, very similar. And then you'll work on the projects during the rest of the semester. What will be the deliverable? A 4-minute presentation, a talk where you'll discuss what data you selected, what the idea of the project was, what kind of analysis or what kind of goal you had in mind, what parts of the course you used. Did you use Hadoop, Pig, Kafka, Spark, MapReduce, or something else that comes later? And then the results, what was the final result of the project? It'd be marked on difficulty, appropriateness, scale, good use of techniques, presentation, how interesting the project is, creativity, value, sort of like what's the overall value of the output. So one thing to distinguish here, to mention, is that ambition is appreciated even if you don't succeed. So in general, I would rather prefer a very ambitious project where you kind of get like 70% of it done and it's, you learn a lot from that, rather than a simple project that, I don't know, counts the words in a very large file, where you do it 100% perfectly, but the ambition was not all that high, let's say. So ambition is appreciated. That's not to say that you need to try to do the most difficult thing in the world or anything like that, but it's taken into account in the marking. So yeah, if you want to be ambitious and fail spectacularly, that's appreciated. So in general, what are the overall kind of ideas of the project? It must focus around some technique from the course. That's the core criterion. So it's essentially you have to use something that you've learned from the course. So it has to involve Pig or Spark or MapReduce or Kafka or some of the other things that we'll see later in the course, some NoSQL system, Elasticsearch, Giraffe, Apache Giraffe, some of the other frameworks that we'll look at. The expected difficulty is similar to a lab, but without. So I must say here, the technique is more important than the system. So if you wanted to use an alternative system that we've not covered in the course, but is somehow related or maybe an alternative to something that we've seen in the course, that's also perfectly fine. For example, if you wanted to use a streaming platform like Flink instead of Kafka, that's perfectly okay as well. Or if you wanted to play around with Spark SQL or data frames or whatever, that's also fine. Expected difficulty would be similar to a lab but without any instructions. So, if you think about the last couple of labs you've done in terms of analysis, that would be kind of the type of depth of analysis that would be expected if you go down the road of a data analytics project. Data should not be too small, so it's about processing large amounts of data. So you should have maybe at least about 250,000 tuples to essentially exercise the part of scale, because this course is about processing data at large scale. On the other hand, the data should not be too large. I mean, you can have data that are as large as you want, but if you're using the cluster, it would become difficult. So for sure, there should be less than 1 billion rows. It depends on what you want to do, but if it's a very large data set, you can perhaps work with a sample. And this is mainly just for, okay, first of all, so that your processing in your project doesn't take, several days, but also so that the cluster doesn't get filled up too quickly or too easily. If you want to work at very large scale, you can look into options for working locally, if you happen to own a cluster of machines, or for renting machines on the cloud, on Google Cloud, Amazon EC2, or something like that. If you have access to those sorts of services, then that's perfectly fine. But I would say a sweet spot for data size would be somewhere in the area of maybe 1 to 10 million, 1 to 10 million tuples. If you want to work with smaller data, in the case of particularly interesting projects, for example, if you wanted to do something relevant to COVID-19 data or to the constitutional process, or you had some very interesting project where you really want to work in it, and it's maybe not so large, we can talk about that. You can send me a mail or something, and we can see if we can make an exception for that. But in general, this would be the expectation for scale. So yeah, these are the overall guidelines for the project. You should work with data at scale. Sorry?
I have a question, sorry.
Yep.
What happens if we work with a stream? For example, we are trying to generate data from something like stocks, maybe the weather or something like that, and we are trying to generate this data. We could try to generate more than 250,000 tuples, but maybe we cannot do that. But we could try to work with streams anyway.
Yeah, so I would say, again, a similar sort of idea would apply, in the sense that if you work with a stream of data, you should work with a high volume stream, a relatively high volume stream, in the sense that you could be processing, somewhere in 250,000 tuples per hour, maybe, or 1 million, 10 million, 20 million, 50 million tuples or inputs per day. So if there's like a one input per second, it would maybe be a bit low, or it would be relatively easy to handle. It wouldn't really justify the use of the techniques we're using in this course. You could store that easily in a dictionary in Python, for example, or whatever. But again, there's quite a bit of flexibility. So if you can justify, somehow that, okay, we have streaming data and we're processing a certain rate, that would be challenging to process by other means, then that's also perfectly fine. I think the more broad general concept is that the technique you use from the course should be justified, in the sense that it shouldn't be easy to do by other means. I mean, if you do some data analysis that you could have done in Excel, that's not so interesting. You know what I mean? Or in a relational database. Okay, that one's maybe a bit trickier, but the use of the techniques from the course should be justified. There is, of course, a trade-off that where the techniques are really justified would be over massive data, like where we have 1 billion tuples or 1 billion lines. But then it just becomes really, we run out of resources, and maybe the project becomes a bit tedious because you have to wait several days for even simple analyses. So yes, it would be great if you can work with streaming data, but it would again be the expectation would be to process a good volume of data as a stream.
Okay, thank you.
Okay. Any other questions or doubts? Okay. Where to explore or find data. If you're looking for ideas, you can play around on Kaggle. It has some larger data sets, small data sets, large data sets. Google dataset search, you can search for particular topics and see what sorts of data are out there. Kaggle is better for kind of exploring random data sets. Google dataset search may be better if you have an idea in mind of a topic and you want to find what data sets are available on the web. There's also some local data sets, and really interesting local data sets about Chile. So you can find some data in the local platform relating to laws and policies and congressional discussions and so forth. And more besides. You can have your own, you might take data from a company you've worked with, you might take data from your PhD, your master's, whatever is of interest to you. Yeah. So that's it. Any questions or doubts? Okay, so in the lab on Wednesday, we'll play around with some Twitter data in Kafka. And we'll be processing streams of tweets using Kafka, trying to detect certain events. So see you on Wednesday if there's no other questions or doubts. Oh, something in the chat. Sorry, did I see? So you could work with your Arduinos if you want to create a cluster of Arduinos and install Hadoop or something on them. I'm not sure. There might be an interesting project, but you'd have to work with lots of data. I mean, it would be interesting to see how much data you can process on 4,000 Arduinos, for example. That would be cool. Or streaming data from the Arduinos as well would be good. Maybe you have Arduinos producing streaming data that you are processing using Kafka. So what I can do as well, by the way, is post a link to the project presentations from last year, so you get some ideas, maybe for different types of things that were done. Okay, so see you on Wednesday.